Can everybody hear me up there? Can you hear me? Okay. So I see attendance is kind of sparse today, so we'll take attendance. How about that? It's always a good algorithm. Last time we talked about decision versus optimization. We said that deciding whether some condition is true or not, it's about as easy or as hard as actually finding a solution for that condition or that stipulation. So for example, determining whether a Boolean formula is satisfiable is as easy or as hard as actually finding a satisfying assignment. And that situation, counterintuitive though it is, because you would think it's harder to find a solution, just determine whether a solution exists for something. That situation is occurring because in general you can play 21 questions with a decider and thereby turn it into an optimizer. Right? Just like if you ask me 21 questions about which animal I'm thinking about, and I'm not going to tell you the animal, eventually you'll know it's a zebra if you ask me enough questions. And that's true in general. So that induces the class NP, basically. Class NP could be alternatively characterized as the class of problems for which you can prove that an answer exists. Okay, well, never mind finding it through 21 questions. So just so you don't see NP in isolation, I'm showing you a whole bunch of other complexity classes around NP, inside NP, outside of NP, just so you can see some of the landscape around it, computationally speaking. So, here's the class of polynomial time, deterministic polynomial time solvable problems. That's P. So for example, you can determine whether strings have this form. You can test for primality. You can do linear programming. A lot of things you can do in P. The NP is right outside it, and there's the NP-complete problems. P and NP could be the same, and we don't know it. This is a Venn diagram. This is a set containment diagram. So these ovals represent sets and subsets. These subsets are not necessarily proper subsets. So in the case of P and NP, we know that P is contained in NP. We don't know if they're equal or not. But for example, in P versus x time, exponential time, so polynomial time and exponential time, we know that they're not the same. So some subsets here, shown in this Venn diagram as containments, are proper subsets. Other ones, we know they're not proper subsets. Some we have open questions about. We don't know if they're proper or not properly contained in other subsets. So there's a lot of open questions in this diagram that you're staring at. Right, so here's polynomial space. Polynomial space could be equal to P, to polynomial time. We don't know. It's not likely, because that's even a bigger class than NP, and we don't even know if P and NP are the same, much less P and P space are the same. Because if P, polynomial time, and polynomial space are the same, NP, that's sandwiched in between them, will be equal to all three. And that will solve that open problem. So there's a lot of open problems here. Exponential time we know is not the same as polynomial time. There's space and time hierarchy theorems, which we're not going to go into in this class, but in a theory class we would go into them and even prove them. The space and time hierarchy theorems basically say that if you have enough more space or enough more time, you can solve more problems, provably so. The complexity classes are not the same. Okay. Let's just leave it at that. And then, of course, things are decidable within any finite time. And there are things that are undecidable because no finite time will suffice because there's no algorithm for them. Like the holding problem, we already proved that way early in the course. The holding problem has no algorithm, no matter how inefficient. Some problems are so hard to compute, not only they'll take enormous amounts of time, it's worse than that, no time will suffice because there's no algorithm for them. So things can get worse and worse and worse, and there are things that are even worse than that. Right? You can show that there are problems that are undecidable, even if you can solve the halting problem in constant time, which there's no algorithm for in any time. Even if you can solve the halting problem in constant time, you can mathematically prove that if you had such a subroutine, you can solve the halting problem in constant time. There are still problems so hard that even if you're using that halting problem in constant time solution as a subroutine, you still can't solve the other problems. So they're even more undecidable than the halting problem. So it's a whole infinite hierarchy of undecidable problems, some of which are more undecidable than others, which is an interesting concept. So we're saying some things are impossible, but other things are even more impossible than that. In what sense? That even if you could do this first impossible thing freely, at no cost, instantly, you still couldn't do the second impossible thing with arbitrary number of calls to the first subroutine that solves that impossible thing. It's a very mathematically precise statement you're making. So there's degrees of impossibility, amazingly enough. How many knew that? Oh, almost nobody. Oh, my gift to you. Read about it. Extra credit. Tell me what you learned. Wikipedia. Okay, any questions about this map? This is kind of it's a Venn diagram. It's also kind of a map of the landscape of certain complexity classes that we know and love, including P and NP right here, but there's lots of other ones. Just for the record, context-free languages are in here. They're a subset, proper subset of P. Context-free languages are languages like palindromes, recognizing palindromes. You can do it with a stack. You can't do it with a finite automata only. Right. And there's deterministic context-free languages. There's regular languages that are made of regular expressions. Those you all know and love. We use them all the time. Regular expressions, they're proper subset of P. They're regular languages. And of course, there's finite languages. And there's infinite hierarchies between these classes. Just so you don't think that this map is all there is. I'm just showing you the most common couple of dozen complexity classes here. But there's literally hundreds and hundreds of complexity classes that are known and named. They have special names because we study them all the time, of which P and NP are just two of these hundreds. So here I'm just showing you a few dozen. And there's infinite number of classes in between these infinite hierarchies. So I'm kind of showing it to you diagrammatically in purple and in red kind of bullseyes kind of notation there, just so you know there's a whole lot of stuff that this slide is too small to contain. Otherwise it'll get really messy. And in the theory class and in complexity class, you go into a lot of these other classes of problems and types of complexity classes and their relationships and their non-relationships and containments and so on. Okay, but back down to P and NP. At least once you should see the bigger picture. So just why I showed you this slide. So we talked about graph cliques. We said you can convert satisfiability, in particular 3-SAT, to a graph clique problem in such a way that the resulting graph has a clique if and only if the original formula that induced that graph has a satisfying assignment. So you reduce the problem of satisfiability to the graph of graph cliques. And independent set, similar reduction. We know that independent set is the opposite, the antithesis of a clique. It's an anti-clique, right? In independent set, no two nodes in that independent set have an edge between them. In a clique, it's the other way. All pairs of nodes have edges between them. And you can convert one to the other. So you can take a independent set solver and convert it to a graph clique solver simply by negating the graph, by inverting the graph, invert edges and non-edges, and then call the independent set solver, and if that gives you an independent set, you know that the original graph had a clique in it. So that's an easy transformation. How many get that one? Right? We talked about it last time, just as a reminder. Okay. Graph colorability is sort of where we left off last time. We said you can take an instance of 3-SAT, and each clause becomes this kind of graph piece or graph construct called a gadget in such a way that this gadget is 3-colorable if and only if that original clause is satisfiable, it's true in the original formula. So you can take an arbitrary instance of 3-SAT and convert it to this big graph in such a way that this graph is 3-colorable if and only if the 3-SAT instance is satisfiable. And so once you have a coloring of this graph that looks like, say, this, the answer may not be unique, you can just read off from the colors what the assignment is. X is true, Y is false, Z is false, and so on. And it gives you a satisfying assignment, and then you can go and check it, and that's how you reduce satisfiability to graph coloring instance. Bottom line is, if you have a solver for graph colorability, even just 3 colorability, not any old colorability, which is even more general, graph 3 colorability, the 3 colors suffice, this construction will enable you to solve arbitrary SAT instances in polynomial time, assuming that the graph colorability subroutine works in polynomial time too, because this transformation is polynomial. In fact, it's not just any old polynomial. How fast is this transformation converting the original SAT instance into this graph. Big O notation. Let's say you have a formula of size n. There's n variables and negations of variables, and generally it has n literals in the formula. How big is the graph as a function of the formula? The formula size being n. It's big O of what? Take a wild guess. How many say n, linear? Yeah. Okay. The rest of you have no opinion? Okay, that's okay. Why? Because every clause ends up as a small fixed piece of the graph. Roughly what? 1, 2, 3, 4, 5, 6, 7, 8 or 9 at most, nodes, however many it takes. So it's a linear transformation. Even if it was quadratic, it'd still be okay. Even if it was degree 17, it'd still be okay. But it happens to be linear. I just wanted you to observe that. Okay, so you might ask, what makes colorability difficult? Why is it so hard to paint the nodes of a graph in such a way that no two neighboring nodes share the same color? It sounds pretty innocent, right? Straightforward, kind of a task. What makes it so hard that humanity doesn't know of a polynomial time algorithm for it yet, or ever? And you might say, okay, here are some graphs. We three-colored these graphs. Why is it so difficult? Is it the high degree, perhaps? What if we restrict the degree of the graph to some low degree? Maybe it's nodes of this kind that have degree 6 or 10 or degree 100. Nodes can have arbitrary degree in a large graph. Maybe it's a degree that's the problem. And so we try to reduce the problem, simplify it, and see how hard it remains if you say lower the degree. The answer is no. Graph colorability is hard even for max degree 4 graphs. But it's easy for lesser degree. So if you say, if the maximum degree of a graph is 0, colorability is real easy. If I ask you if a graph of degree max 0 is, say, 3 colorable, how hard would it be for you to determine that it is or isn't? Degree 0. It's always 3 colorable. In fact, it's always 2 colorable. In fact, it's always 1 colorable, right? Because there's no edges. If the degree is 0, there's no edges at all. So you see, if you reduce the degree enough, it becomes a trivial problem. Nothing hard about it. Okay. What about degree 1 graph? If I give you a degree 1 graph, maximum degree 1, could be some nodes can have degree 0, other nodes can have degree 1, and I ask you, is it 3 colorable? You say there's a simple algorithm for it. Yeah, what's that simple algorithm? If I say a degree 1 max degree 1 graph is 3 colorable, yes or no, what's your algorithm? Let me give you a hint. It's 1 line long, 1 line of code. So the question is a yes/no question. It's a Boolean query. So I give you a graph that's degree max 1 degree, maximum. Every node has a degree at most 1. The question is, the yes/no question to you is it 3 colorable? Your algorithm is what? Return true. How many get that? Yeah, very simple, 1 line. Right? Return true, and you'd be right. You'd be right all the time. Any questions about that? It's so easy, it's almost hard because it's so easy. All right, if I say a degree max 1 graph, is it 2 colorable? Yes, how many see the answer is the same, algorithm is the same as before? Okay. Degree 1 max graph, is it 1 colorable? Now it's not as trivial. You have to check for what? If there are any edges. If there are any edges, it's 2 colorable, but not 1 colorable. So the algorithm is slightly more complicated than trivial. Trivial report true end. What if I give you a degree max 4 graph? I ask you, is it 3 colorable? What's your algorithm then? If time wasn't an issue, you can use all the time you want, what's an algorithm then? A simple algorithm to tell me if the degree max 4 graph is 3 colorable. Try everything. Brute force. Brute force is always a trivial algorithm that works if you don't care about the time, the complexity, how long it takes. But if I ask you, is there a polynomial time algorithm for this? Nobody knows. That's an open question. It's been open for 50 years. It's equal to P is equal to NP. Equivalent question. So things get subtle very, very quickly. 0 was trivial, 1 was trivial, 2. And then it's NP complete for 4, max degree 4. And by the way, what about max degree 2? We haven't talked about that specifically. If I say if a graph has max degree 2, is it 3 colorable? How many say, yeah, it's always 3 colorable? Yeah, why? Max degree 2. Why is it always 3 colorable? No exceptions. Not completely out, yeah. Yeah, we're getting to that. Yeah, that's a deeper dive than I intend right now. But if the max degree 2, it's always planar and 4 colors will suffice. True statement. But I ask, is it 3 colorable, not 4 colorable? Yeah, but you're right, and we'll get to that in a minute. So again, if a graph has max degree 2, is it 3 colorable? How many say, yeah, it's always 3 colorable, max degree? How many say, no, there's exceptions? Okay, so majority said, yeah, it's 3 colorable. Why? What do graphs of max degree 2 look like? What's their structure in general? We already said if the max degree is 0, it's just isolated nodes. If the max degree is at most 1, it's what? Isolated nodes or pairs of nodes. Yeah. Could you have 3 nodes connected up together and have max degree be 1? No. Because that'll make one of them degree 2. But max degree 2 graphs, what do they look like? What's their structure? Obviously, you can have isolated nodes. You can have pairs of nodes. You can have cycles. How many see that? Cycles. Or long chains. Can you have anything other than isolated nodes, pairs, chains, and cycles? Right. A pair is actually a chain of size 1 or 2. Right? Can you have other things in a max degree 2 graph other than isolated nodes, chains, and cycles? I mean, say, yeah, you can have something else. I mean, say, no, that covers it. Yeah, that covers it. Can you paint all these things with 3 colors at most? Cycles, chains, and isolated nodes? I mean, say, yeah, you could. Yeah, you could. Why wouldn't it take more than 3 to paint, say, a chain? How many colors will it take to paint a chain? 2. A cycle? At most 3. Or 2, but at most 3. Why 3? What cycles take a 3rd color? Odd cycles. So a max degree 2 graph requires 3 colors at most, and the only cases it does require 3 colors is when it has odd cycles. It's an if and only if. That's a theorem. And we just proved it. So your algorithm is very simple to determine if a max degree 2 graph requires 3 colors. The answer is always yes. If it requires only 2 colors, the answer is a little more complicated. You got to check for odd cycles. How many get this algorithm? Okay. So you see, you reduce the degree enough and it becomes trivial, or not quite completely trivial, but still pretty straightforward. You keep the degree 4, and that's NP-completeness in full bloom. It just blossoms into arbitrary complexity not known to be in polynomial time. That's the threshold. I'll leave up to you what happens with degree 3. I left that out. For extra credit, tell me what the situation is with degree 3. Is it polynomial time solvable? Or is that already also NP-complete? But now, we're going to show that graph 3 colorability is NP-complete for these maximum degree 4 graphs. So solving maximum degree 4 colorability is as hard as solving arbitrary colorability of any degree, which is very interesting. It's kind of unexpected, because you reduce it enough, you trivialize it. So sometimes you look for the threshold of complexity, where complexity rears its ugly head and metastasizes into full-bloom complexity from straightforward polynomial time, And for degrees, it happens at 4 for colorability. For other problems, it happens at other thresholds. It's interesting to explore where the problem just explodes into full blooming complexity of very high order, but possibly exponential time, where this explosion occurs. It illuminates the nature of these problems. Okay, so we're about to prove that degree 4 max graphs, it's NP-complete to 3 color them, whether there's even a 3 coloring for any given max degree 4 graphs. Here's the proof. So we're going to use a gadget that looks like this. This gadget has several properties that are important to us here. So first of all, it has max degree 4. How do we know? Because you can just look and see that the degree is never more than 4 anywhere in this gadget. In some places, it's even less than that. So the degree is 4 at these circles, and here the degree is 2. The gadget is 3 colorable, but it's not 2 colorable. Why is it 3 colorable? Because here's a 3 coloring of it. That's a 3 coloring of it. It's a valid coloring. So why is it not 2 colorable? Well, there's a triangle here. And we know that no triangle is 3 colorable, because that's an odd cycle. Odd cycles require an extra color. Two don't suffice anymore. Okay, that's the second property. The third property, in all 3 colorings that you come up with, the corners get the same color. So that corner and that corner and that corner, these 3 corners will all get the color blue. There's nothing magic about blue. It could be green, it could be red, but all 3 corners will necessarily have the same color. That requires a bit of a proof. So there's this kind of 3 colorability constraint propagation. It works like this. If you have a diamond-shaped subgraph that looks like this, just 4 nodes connected like a diamond, opposite corners will have the same color. Why? Because once you paint this to the first color, this has to be the second color, that has to be the third color, and that guy below has to be the first color again, the same as what you started with. How many get that? So it's unavoidable. So opposite corners of the diamond must have the same color in any valid 3 coloring of the graph that contains that diamond shape. Not just the diamond shape itself, but the entire graph. Once you 3 color it, each diamond in it must have this property, because it's colorability constraints. So this constrains this and that. Both of these constrain this, and both of these constrain that, and that must be the same color as the first. It doesn't necessarily have to be red. The 2 ends could be blue, or the 2 ends could be green. Colors are interchangeable. You don't have to call them red, blue, and green. You can call them 1, 2, and 3. You can call them alpha, beta, and gamma. You can call them Larry, Moe, and Curly. It doesn't matter what you call them, as long as you call them something. Right? So, given this propagation constraints, whatever the middle node is, notice there's a diamond here. This diamond here is the same as that. So whatever that node is, its color will be the same as that corner. How many can see that? Because it doesn't matter which way it's oriented, colors propagate according to this constraint. And same here, there's a diamond here. So this color propagates here, and once you do that, these other ones are determined, right? There's a triangle here, so both of these must be opposite colors. So without loss of generality, because it's symmetric, we'll make them blue and green, not red. Once you do that, these other ones are determined, because this has a blue neighbor, this has a red neighbor, so this must be green too, and this must be green too. These red arrows show you how the constraints, the colorability constraints, are propagated out to other nodes by their neighbors. Once you do that, these 2 impose the blue color on this node. Once you do that, these 2 nodes impose the red color on that node, and all 3 corners, therefore, must be the same color. How many get this proof? It's a proof. It's a lemma, really. Lemmas are just short theorems on the way to bigger theorems. Okay, so this proves the third property. In any 3 coloring, all corners get the same color, red, red, and red. So now we're going to take these gadgets and duplicate them and connect them up into larger gadgets. So we'll take this gadget here that we can 3-color and duplicate it and connect them by the end, connect them by the corner. So now we have a bigger gadget made of multiple copies of this small gadget. But this bigger gadget inherits the properties from the small gadget. And the properties are, so consider this gadget to be kind of a super node. You'll see in a minute why I'm using that phrase, super node, or meta node, however you want to think about it. But it has a max degree of 4. How do we know? We can count the degrees. It's nowhere greater than 4. They're connected by the edges, and each gadget has the edge degree there on the corner of 2, so 2 connected by the degree of 4. It's 3-colorable, but not 2-colorable. How do we know? Because, well, each gadget is 3-colorable, so connection, a bunch of gadgets by the endpoints is also 3-colorable. It's not 2-colorable because it's got lots of triangles. No triangle is 2-colorable, much less anything larger than that. And finally, in any 3-coloring, all corners now must get the same color. By corner, we mean all the tips, the remaining tips. This one, this one, this one, this one, and that one all must get the same color. How many understand that or believe that? Okay, why is that? No matter how many copies we put together, end to end, if you 3-color the entire ensemble of copies, all the corners must all have the same color. How is that inherited from the single gadget instance? Not a trick question, it's straightforward. Yeah. Yeah, in each gadget, the 3 corners must be the same color, but this gadget and that gadget overlap by a corner, so that gadget and that gadget must have that corner in common, and each one must have the other corners in common with that corner, so all the corners constraints propagate out across this entire sequence of gadgets, all connected end to end. How many see that? Yeah. So now we have a larger gadget that has more corners. You'll see in a minute why we're doing this. So far, it's a bit of a mystery, I agree. I'm just laying down the properties so then we can exploit them properly. So now we're going to use these super gadgets or super nodes as fan-out components to reduce the degree of a graph. Okay. So what does that mean? Let's say we have a graph that has some node with a higher degree than 4. In this case, say degree 5. And this is just a piece of a graph. There's other things connected. It could be a very large graph. But let's just focus on this node with high degree, higher than 4. I'm going to replace that node with this super gadget in a way that preserves the 3-colorability of the surgically manipulated graph. In other words, if the original graph is 3-colorable, it's 3-colorable if and only if this new graph with this surgical replacement of this node by a gadget will be 3-colorable also. Let me show you how to do it. So take this node. Here are the 5 edges coming into it. 1, 2, 3, 4, 5. Here are these 5 edges. The remainder of the graph I'm leaving intact. I'm not changing the remainder of the graph. I'm just focusing on this node, doing a local replacement. I'm replacing that node locally, not globally connected to anything else. Its neighbors stay the same. But instead of that one node, I'm kind of zooming in on that node. Instead of having that single node here with the 5 edges going into it, guess what I'll do? I'll put a gadget in here, just like that. This big gadget will replace this node. How many see this replacement happening? Good. Now, why did I do that? Because if I'm going to, but now, first of all, let's see what I did. I replaced that node with a gadget, which means the degree everywhere inside here is at most 4 now. Why? Because I only connected these external edges that came into that node to the endpoints, to the exterior points of the gadget, which had degree 2 to begin with. Every node on the exterior, this one, this one, this one, this one, and that one all have degree 2. So if I connect an external node to it, the degree goes to 3, and the degree everywhere else in the gadget remains the same because I'm not modifying, connecting anything to the internal pieces of the gadget, just to these endpoints. So the degree is at most 4, not 5 anymore, in the neighborhood of this node. And I can do this replacement for every node that has degree higher than 4. I can do this local replacement. I may need larger and larger gadgets. This gadget has 3 copies, but if a node has degree, I don't know, 17, I'm going to need 15 of these gadgets. all strung together into a super gadget to do the local replacement for a node of degree 17. How many see that? Yeah. Okay, so I'm reducing the degree of the graph to at most 4 by doing these local replacements of nodes of higher degrees than 4. It's all local replacements. But more than that, the resulting graph after all these local replacements is 3-colorable if and only if the original unmodified graph is also 3-colorable. How many can see that? Why? Because before I made the replacement, all these 5 edges here come in and see a single node with a single color as far as constraints go. Here, they come into this gadget and they all see exactly the same color internally here, because all the endpoints of the gadget must have the same color. We already proved that. So they behave as a single node with respect to outside colorability constraints interacting with that local group. How many understand this trick? So this Jedi trick is the key to this whole proof. Replacing nodes of higher degree with these gadgets that preserve colorability constraints, same as individual nodes would. But the degree now is much lower of this new graph with these local replacements. And that's pretty much the proof that colorability of degree max 4 graphs is as hard as arbitrary degree graphs. Why? Because you can always use these local replacements. That's a transformation. That's the reduction of one to the other. How many understand this whole thing end to end? And it's maybe a quarter of the class. Okay. How many understand what we're trying to prove to begin with? Never mind how. Okay. It's about half the class. I'll take it. How many here are even listening to me? Don't answer that. Some things you probably don't want to know. So again, what have we done? We're trying to prove that max degree 4 colorability is as hard as any colorability. How do we do that? Well, by taking higher degrees, reducing them to lower degrees in a way that preserves colorability constraints. In such a way that the resulting graph, after all these local replacements of high degree nodes by these gadgets, will be 3-colorable if and only if the original graph was 3-colorable. Okay? So if you had a solver, a fast solver for max degree 4 colorability, all you can do is tell you colorability yes, no, for max degree 4 graphs. For any higher degree graphs, it will choke, it will fail, it will crash, it will not answer. Well, you can exploit this solver, limited though it may seem, into solving any degree colorability for you by converting it to this kind of low degree graph first, and then fitting those graphs with this solver that can only handle max degree 4 graphs. And if you can do its job efficiently, you can solve any graph colorability efficiently. Because this transformation is very fast. How fast is this transformation in terms of the size of the graph? I have a graph of size n, and I want to make all these local replacements. How big is the new graph? First of all, how many see the new graph will be bigger than the old graph? Because you're replacing individual nodes by groups of them. Okay, how much bigger? Big O of what? If there's n nodes in the original graph, n nodes and edges, how big is the resulting graph after all these substitutions? Local replacements. Big O of n. How many see it's linear time transformation? Sure. Because every node gets replaced by, as many of these groups in the gadget as there are edges. But it's only a constant per edge. Right? So it only increases the size of the graph linearly. And even if it did quadratically increase the size of the graph, that's okay too. I just wanted you to see that it's not even quadratic, it's linear, even though it'd be okay if it was n to the 5th. But it isn't, it's linear. Okay, so it's a pretty straightforward, fast transformation. Any questions about this? Okay, so this proves that graph coloring is hard, but not because of the degree. It's hard even for limited degree, 4 limited. Max degree 4, that's still hard, it's still NP-complete. So in a sense, we've reduced all of NP to max degree 4 graph colorability. 3 colorability of max degree 4 graphs. That's as hard as any problem in NP, amazingly. So it's not about the degree. something about colorability that's hard beyond just a fixed degree. It's just difficult even for a small fixed degree. So let me show you an example of how this might work. Here's a graph with one node has degree 6 and one node has degree 5 here. So just so you can see exactly these transformations, how it works. So I'm going to copy the graph here. And I'm going to focus on this node here that has degree 6. And this node that has degree 6 will be replaced by a gadget. So I'm going to take the node away, right, and instead put the gadget in here. And it's a little warped so it fits in the circle. It doesn't matter if it's warped. Graphs are topological, not geometric. Right. And now I'm going to take these edges connected to that node and connect them to the ends of the gadget, like this. Fun with PowerPoint. It's, I gotta have fun doing something on weekends, and now you know what I do. PowerPoint is my hobby. Well, one of several, but still. So now all these nodes are on the outside connected to the ends of the gadget, and that's the replacement there. And I do the same thing for this other node that has max degree. Here it has degree 5. I'm going to make it max degree 4. How? By replacing that node with a gadget. Then all these edges are connected to the ends of the gadget, preserving the colorability constraints that go with it. Bottom line is this original graph becomes this new modified graph here. This has max degree 6, or it can be even higher. This has max degree 4 no matter what. And then I feed that to my max degree 4 colorability solver for 3 colorability, and that will tell me what's going on with this colorability of any graph of any degree. So that's an example of what we did on a previous slide, showing exactly how you do the substitutions. And this is a general construction. How do we understand that now? Okay, good. More than half the class. A win. That's good. It's a good day. And this transformation is pretty straightforward. It works in all cases. And now you have a max degree 4 colorability solver that can do any colorability solutions for any graph. Bottom line is, the problem is NP-complete, even if the degree is restricted to be 4. Any questions about any of that? And why is it 4? Why didn't we go for 3 or 2 or 1 or 0 degree? Well, because those are easy. Those are obviously straightforward algebra like we discussed 10 minutes ago. You can solve that either trivially or with looking for odd cycles or whatever. So 4 is the threshold of where the degree max limit explodes into full bloom NP-completeness. Not at 1, not at 2, and not even at 3. Although for extra credit, tell me exactly why 3 is not NP-complete. Because if 3 was NP-complete, we'd prove that instead of 4. Okay. So colorability is hard. And you might say, okay, well, so the degree doesn't matter. It's hard no matter what the fixed, constant, bounded degree is. What about planarity? Somebody mentioned planar graphs earlier, which is insightful. Now we're going to talk about planar graphs. It turns out for planar graphs, it's still NP-complete. And planar graphs are a very small, special category of graphs. Graphs that you can draw in the plane without any edges crossings, without any 2 edges crossing. Question?
They said that the degree above 4 explodes, but is that a function of colorability as well? Is it a 4 max degree graph, 4 colorability?
So he's saying, so we proved that 3 colorability of degree 4 graphs, of max degree 4 graphs is NP-complete. So he's saying, what about 4 colorability of max degree 4 graphs? Is that NP-complete? How many say, yeah, that's NP-complete too? How many say, no, that's easy? Well, nobody's having an opinion. It must be a good question if nobody can say yes or no to that question. Short answer is it's also NP-complete. If you keep increasing the degree, it gets harder, not easier. If you get more color options, in general, no. Why? Prove to me that even if you ask the question of general graphs, whether a general graph is 17 colorable or not. Why is it not easy all of a sudden for arbitrary graphs? Very good question. Can anybody think of a proof why asking the question whether a graph is 17 colorable, that's still NP-complete? So I'll give you a hint. One common trick you can pull. Let's say you have a graph, and you know you're trying to determine if it's 17 colorable, and let's say it's hard to determine, and you know it's not 18 colorable. Oh, let's put it that way. You know it's 18 colorable, but you don't know if it's 17 colorable. One thing you could do is you could take your graph and also take a 17 clique in addition to the graph, and then feed it to a solver. The 17 clique is not going to be any less than 17 colorable. But you can ask these kind of questions of a solver, and determine the threshold of colorability by deliberately adding pieces to this graph that are not k colorable for some k, and to see if the colorability breaks down because of that piece or not because of that piece. So that's one thing you can do. But generally, let's just say the higher the constraint, in general, the more difficult it is to determine. And the lower the constraint, maybe you could play some tricks and have some bounded number of choices, or in the case of constraint 0, 1, and 2, the algorithms actually trivialize to whether it's chains and odd cycles, or have edges or no edges in the case of 1 and 0. So in general, the more general the constraints, the more difficult the question becomes. Because the ones with restricted constraints is a special case of the general case, right? So if you had no constraint, so you should probably leave it at that for now. Yeah.
And is a n-degree graph always n-colorable? Is that always?
Yeah. An n-degree graph is saying is always n-colorable. Sure, because you can paint all the nodes different colors, 1 to n, and it doesn't matter what the edges are. No two nodes share a color because they all have different colors. So yeah. So when you increase the constraint, to high enough, well, if you remove all the constraints at all, and you ask if a graph is n-colorable, it becomes trivial again, simply because you can paint every node with a different color. Okay. But if you make it a smaller threshold, it's not so obvious how to pull it off if it's possible. Yeah.
A triangle is a 2-degree graph, but it is not 2-colorable.
A triangle is a max degree 2 graph, but it's not 2 colorable, but it is 3 colorable. It requires a third color because it's an odd cycle.
Yeah, so means the statement was a bit.
Well, so for special cases, you can kind of reason it out, and if the constraints, not necessarily just the degree, in other, or just the number of colors. Generally, if you restrict a parameter of a problem to be a very small range, the problem gets easier, not harder. In general, there's probably some counter examples to that, but that's a general trend. Okay, let's talk about planar graphs. So if a graph is planar, if and only if it can be painted in the plane, put all the nodes in the plane, and all the edges can be put also there such that no two edges cross. That's a planar graph. So this graph is planar. So we're going to show that it's NP-complete whether a planar graph is 3-colorable or not. So it's not about planarity either. And planar graphs, by the way, are a very, very special case of graphs. In a planar graph, you can only have linear number of edges, not quadratic. In general, you can have quadratic number of edges. You can have all nodes connected to all other nodes. It's n choose 2 nodes, which is n squared nodes. n squared edges on n nodes. So the number of edges can go quadratically in the number of nodes. For planar graphs, they both grow linearly in one another. So that's already a huge constraint on the types of graphs that are planar versus non-planar. So we're going to use a planarity preserving gadget. So the essence of the proof is similar to the previous proof. We're going to do local replacements by gadgets in a way that preserves colorability. So now it's a little bit more involved than before because we have to properly respect planarity, not just the degrees. So the gadget is planar. Why? Here's a planar embedding of the gadget where no two edges cross, obviously. It's three-colorable. How do we know that? Well, because here's a three-coloring of it, a valid three-coloring of it. So this gadget is planar and it's three-colorable. And in any three-coloring, opposite corners get the same color. So whatever this color is, it'll be the same as that color. And separately, whatever the leftmost color is, it'll be the rightmost color on the other end, independently of the first pair. And this requires proof. That's not obvious. So first we notice whenever you paint the original center, let's call it red arbitrarily without loss of generality, its two neighbors over here will be the other two colors. So color 1, color 2, and color 3. And then you start having constraint propagation of colorability. Remember that diamond that constrains the two ends of the diamond, top and bottom, to be the same color from a couple of slides ago? Well, there's a lot of that going on here. How do we know? Well, here's a diamond here, right? This diamond here, right? So this color propagates down here because of this diamond. How many can see that there's a diamond here that looks like that? Even though it's a little bit skewed, that's fine. It's topological, not geometric. So these colors propagate out. So whatever you paint this color with, that will enforce. There's two choices now. What we're going to do is bifurcate into two choices where this is green or this is red. If this is green, this guy is constrained to be red by these two neighbors, right? And then this guy is constrained to be blue by these two neighbors, right? And so on. And all the colors begin to propagate around in a forced way, right? Every two neighbors force their neighbor to be the third color other than themselves, because that's what colorability is about. And you have these bunch of forced choices now. But the point is that whatever color this was, green, this will acquire the green color as well by all these propagation of constraints. Not only that, whatever color this was, blue in this case, this will become blue as well by a similar propagation of constraints all the way around. And finally, this one will be red. So the other case is if this was painted red, not green. That was the alternative case. And you'll have a similar propagation of constraints there. If you follow the constraints, everything is automatically forced to be painted these following colors. And you can have, but the bottom line is that this end and that end must have the same color. And separately, this end and that end must have the same color. Okay? And they could both all be the same as each other, all four of them. But that's a special case. But generally, this configuration propagates this color all the way out to here. How many can see that? Okay, pretty straightforward. Right? And that'll be the gadget for substitution, for local replacement that we'll do in arbitrary graphs. And notice that, so opposite sides are independent. So this color is the same as that color. Separately, this color is the same as that color. And they can all be the same color, but there could be also different pairs of colors. So you have this kind of independence of opposite pairs, which are the same as each other, but independent of the other opposite pair, which is the same as each other for the opposite pair. You'll see in a minute why that's important. Okay. Once you wrap your mind around this gadget, we're going to use it now to do local replacements. And here's how we're going to use it. So I'm going to basically eliminate edge intersections in a non-planar graph using this gadget to preserve colorability constraints. So let's say I have this non-planar graph. And by the way, this graph happens to be technically planar. I'm just drawing it in a non-planar way. How many see the difference? How many can see that this is actually a planar graph if I chose to draw it differently? Yeah. How would it be planar if I chose to draw it differently? Yeah, I could take this line, this edge here, and just draw it the long way around instead of cut. But let's just keep it this way. You'll see in a minute why it doesn't matter. Some graphs you can't do this. No matter how you redraw the edges, it's not going to make it planar. All right, so we have two problems of crossing edges right there and right there. And we're going to use local replacement with this gadget to handle these cases, these edged crossings there. So what I'm going to do is replace those crossings by these gadgets. So I'm going to focus on these two locations here and replace them by this gadget, each one of these edge crossings by a gadget, and then reconnect the nodes. Instead of connecting across the gadget, I'm going to connect it to the endpoints of the gadget. So this neighbor here is going to connect to this endpoint of the gadget, and the other endpoint is going to connect to the other endpoint using diamonds, right? So I'm going to connect the gadgets up by the diamonds. Why diamonds? Because diamonds preserve the colorability across the tips of the diamond. So whatever that color is, this must be the same color across the diamond. So by connecting things with diamonds, I'm preserving the colors. If you were to three-color the whole thing, the diamonds will be three-colored properly, and the constraints, more important, will be propagated out in the same way as if I didn't replace them with diamonds and gadgets. How many understand that strategy? Yeah. So this is a brilliant way of handling edge crossings by eliminating the edge crossings and instead connecting them with diamonds to their original neighbors, replacing each crossing with a gadget. And once I do that, this new modified surgically manipulated graph with all these gadgets and diamonds replaced is three-colorable, even only if the original was three-colorable. Except now it's planar. The original one was not necessarily planar. So if I had a subroutine that can determine three-colorability for planar graphs and planar graphs only, I can exploit that poor thing into determining colorability for any arbitrary graph without it even suspecting that we're exploiting it to do much harder job. By first converting a non-planar graph into a planar graph, that's three-colorable if and only if the original was, and then using this solver for planar graphs, and it's doing the general job for us now through this transformation. And that's why colorability of planar graphs is NP-complete. It's as hard as colorizing any graph of arbitrary structure, non-planar. How do we understand this proof? Okay, straightforward. Well, once you have the gadget, it's straightforward. I mean, imagine what it took for somebody to concoct this gadget and come up with its properties. You know, that took a lot of rainy afternoons to, you know, scratch your head and try hundreds of things that didn't work until somebody found something that did work and preserved colorability through this local transformation, preserving planarity. I mean, that's clever. That's not trivial. Yeah.
Why can't this gadget be another diamond and it's a major force?
Why can't this gadget be just a diamond and make it a whole lot simpler? Because it's not enough. Some of the constraints will be lost and not preserved, and it won't be an if and only if anymore. And you can try to experiment with smaller gadgets or simpler gadgets or just a diamond. You'll see that you're losing the equivalent constraint propagation of the colors. You'll end up with some graph, sure enough, but you'll lose the property that that graph you'll end up with is three-colorable if and only if the original was three-colorable. It won't be an if and only if anymore. And it has to be an if and only if. Okay. How many understand that? That's a good question. Put it another way, if there was a simpler gadget that works, I'll be showing that to you instead of this more complicated. Because there's much more complicated gadgets that work too. But that's the simplest known gadget that does this job. And people have looked really hard for simpler gadgets or an alternate proof altogether, not even to do with gadgets. Okay, so, and that's how you do it. That's how you solve general colorability with planar only graph colorability subroutine. So if graph colorability for planar graphs, all of a sudden you get some efficient algorithm for that, polynomial time algorithm for that. Immediately you'd have a polynomial time algorithm for arbitrary colorability and for all of NP. Okay. So it's not about planarity, and obviously it's not about maximum degree being 4. So the next question is, what about max degree 4 and planar at the same time? Throw both constraints onto a graph. Make sure it's planar, make sure it's max degree 4, because these graphs here, it's not max degree 4. I mean, you can see that the degree could be much higher than 4 once you do this transformation. I mean, it's 5 right here. It's not even 4 here. And here, it could be 5, or it could be 6, or 10, or 20. Whatever the degree here was, that'll be the degree there. So it's not max degree 4, but it is planar. The previous proof, or gadget replacement strategy, was max degree 4, but not necessarily planar. What if it's both? What if you restrict the graph to be both planar and max degree 4? That's a, each one is a big constraint. Put them together, maybe the problem is now easy. Turns out it's still NP-complete. It's max degree 4 and planar at the same time. What do you think the proof would be? Take a wild guess. Yeah, putting both schemes for replacement simultaneously on top of each other. So let's show it to you by example. Let's say I have this max degree, I have non-planar graph because it's edges crossing. So I do this transformation. So I do this transformation that we just saw, and now the graph is planar. But it's planar, but the degree is higher than 4. Here the degree is 5. And it could be here the degree is 5 also. Right? Here the degree is 5. The degrees could be even higher than that. Now I'm going to do the other transformation, the other local replacement from the previous proof from 5 slides ago, and replace each higher degree than 4 with this other gadget that looks like this. And I'm going to keep doing it. I got to do it other places. I'm not going to show it all because there's one here and there's one here and there's one there and there's one there. So then you start getting messy. But I can pull the original transformation on top of this last transformation, and now I have a graph that's both planar and max degree 4. And testing for 3-colorability there is as hard as testing for arbitrary colorability and arbitrary graphs by the same kind of reason. How many understand that trick? Okay. So you can compose these reductions. So what we did is compose 2 reductions. It's a composition of 2 reductions, one on top of the other. Could you have done it the other way around? I'll let you think about that. Could I first replace, the max degree 4 gadgets and then worry about edges crossings? How many say, yeah, I could compose them the other way too? How many say you might run into some issues? What issue might you run into? Yeah, once you do this, and then it may ruin the planarity. So you have to be careful. You can't just compose things any old which way. You have to be a little careful. Okay, but we'll leave it at that. And you have to do this replacement at these other places. I'm just not showing everything because it'll just get messy. I just showed you one replacement. And by the way, how fast is this transformation? If there's a graph of n nodes and edges total, what's the resulting graph size? Oh, and you see linear, not really increasing its size asymptotically by anything. And if you did, it'd still be okay. If it was quadratic or cubic, it'd still be okay. But it isn't necessary to increase the size. Just so you know. So a little more about graph colorability in general. So planar graph one colorability is trivial because a graph is one colorable if it has no edges. Right? We already mentioned that. Planar graph two colorability is not completely trivial, but it's easy. A graph is planar, and a planar graph is two colorable if and only if it's just at most pairs of edges, but not odd cycles. I guess chains are okay too, not just pairs, but chains, but not cycles unless they're even cycles, in which case 2 colors are sufficient to paint an even cycle, but an odd cycle requires 3 colors. How many understand that? So that's relatively straightforward. You can determine that condition quickly. But whether planar graphs are 3 colorable, that's NP-complete. Why? Well, we just proved it in the previous 2 slides. But here's an interesting situation. Planar graph 4 colorability is trivial again. So that goes back to the question you raised earlier. Why? Because every planar graph can be painted with at most 4 colors. That's a known mathematical theorem. It was open for centuries, for a couple of centuries, since the 1800s. And finally, in 1975 or so, 2 guys, Appel and Heiken, finally proved that 4 colors suffice to paint any planar graph. How many have heard of that result? Okay, good. It's a famous result. Major math open problem, open for 150 or so years. beginning in 1852, and then finally they solved it in the mid-70s. Interesting thing about this proof, even though they proved it, that 4 colors suffice to paint any planar graph, that proof required almost 2,000 special cases, analysis of 2,000 special cases. Each one had to be proved and separately established as a lemma before so the proof was hundreds of pages long, maybe thousands of pages long, actually. And it was proof done by computer, because there's no way a human could analyze all these cases and show that there's no other cases but besides these, almost 2,000 cases. It was one of the earliest proofs that were done by computer, and took another computer program to verify. And some mathematicians actually, on principle, object to these kind of proofs that can only be understood second order, second hand, via the program that checks it. Because programs can always have bugs. And the program can say, yeah, I checked this proof, it's working, don't worry about it. Well, you can scratch your head and say, well, what if the program has a bug in it, and just report a false positive on the correctness of the theorem that you checked mechanically. It can get even worse. Right? You can have a program that writes a program that proves a theorem, not just a program that proves a theorem. So you get arbitrarily far away from first-hand knowledge of human understanding. Of course, there's also proofs constructed by humans that are so many hundreds of pages long that only, like, say, six people on the planet are capable of understanding that proof. Right? Like Fermat's last conjecture that became Fermat's last theorem, proved by Andrew Wiles in 1993, finally, after 3.5 centuries of being open. There's only a handful of people on the planet that can understand all 400 pages of that proof. And we all take their word for it. That is true. So already most of what we know is already second-hand knowledge, based on the word of famous mathematicians that we don't trust, that verified it on their own. And this problem was so famous that the US Post Office had this stamp cancellation method back in 1976 when this first came out as a proof, and they said 4 colors suffice. So official stamp by the US government. Must be true then. There were no fake news back then. Sort of. Okay, so another interesting theorem that's finding a planar. So just because we know from that theorem that a 4 coloring exists for planar graph doesn't mean it's easy to find. And you can find a 4 coloring for a planar graph in quadratic time, in deterministic quadratic time. And you can find a 5 coloring for a planar graph in linear time. But that's sort of the best we can do so far that we know of. So we know these colorings exist. 4 colorings exist for planar. The theorem tells us that. But actually finding it is not trivial and could take quadratic time for a 4 coloring, even though we know it's there. Right? Testing for planarity, though, you can do in linear time. I give you a graph. You tell me if it's planar or not. You can do that in linear time. That's a famous algorithm by Lipton and Tarjan from the 1970s. But that's not trivial. It's a complicated algorithm, even though it works in linear time. For a while, it was an open question whether planarity testing can be done in linear time, and it can. It's just hard to do. It's a complicated algorithm. 4 coloring a 3 colorable graph is NP-hard. So that's an even more interesting theorem, because even if you know a graph is 3 colorable, I give you a graph, I tell you it's 3 colorable, for sure. And I'm asking you not even for a 3 coloring, I'm asking you for a 4 coloring of that 3 colorable graph. That's still NP-hard. That's still hard to do. We don't know how to do that efficiently. But we know, for example, that on a torus, 7 colors are both necessary and sufficient. So if the manifold, if the surface is not a plane, but a more complicated surface, like a torus or a double torus, right? So it looks like a donut. Right? That's what a torus is. 4 colors no longer suffice, like in a plane. So here's an example where you need 7 colors. If you take this parallelogram and fold it on itself like a cylinder, this edge will become this edge, because it's a cylinder. And then you connect 2 opposite edges and you get this torus. You see that 4 colors are necessary and sufficient for this configuration. Another way of saying it is if you take this square and you fold opposite sides oppositely together, each color is a neighbor of 6 other colors, which means you need 7 colors. 7 colors are both necessary and sufficient on a torus. Topologically, a torus is the same as a cup. interestingly. Topology is a field of mathematics that is concerned with the global properties of a surface, more generally called manifold, right? And you can have very strange manifolds like Klein bottles and Mobius strips and projective planes. How many even know what these things are? Or good, a bunch of you. Excellent. More power to you. And in general, if you have a surface of genus G, G is a number of holes like a torus or a double torus, two tori or toruses connected together, welded together, or 3 or 4, like a big chain. The number of colors are both necessary and sufficient grows as the square, roughly, of the genus. More specifically, it's exactly this quantity here. So if you have a quadruple torus, 10 colors are necessary and sufficient. Of course, if the genus is 0, you have a plane. So 4 colors are necessary and sufficient. We already talked about that. So in general, you have these more generalized result. Number of colors grows as the square of the number of holes in the surface, interestingly. That we know, that's proven, that's a theorem. So application of graph coloring, there's lots and lots of applications of graph coloring in ways that you don't even expect. So for example, if you want to assign jobs to time slots, you're doing scheduling to avoid conflicts on a shared resource. You want to model jobs as nodes and conflicts as edges. So for example, let's say you have 5 jobs and they're related like this. In other words, any pair of jobs that have an edge between them share some common resource that they cannot collide on. Both trying to access a register on a computer, both are jobs or threads or processes. So you cannot execute things simultaneously that share a resource. Let's say one job is trying to print, the other one wants to print also, but there's only one printer, so both have to wait. So these are mutual exclusion kind of constraints, these edges. So how do you schedule these jobs? Well, it's graph coloring, right? So for example, if you paint, if you three color this graph, you come up with, say, this scheme of 3 coloring this graph. That means job 1 and 3 can execute simultaneously. Job 5 and 2 can execute simultaneously, and job 4 can execute by itself. And so you get this schedule of execution where you have number 4 going first, and then number 5 and 2 in parallel, and then 1 and 3 in parallel, because they don't conflict among each other, those that are running in parallel. So the chromatic number of this graph, the minimum number of colors necessary to paint this graph, is also the number of time slots that you need to maximize your parallelism on this set of tasks or jobs. How many get this? Okay. So graph coloring comes up in all sorts of interesting scenarios that you don't even expect. So you try to do scheduling, you're doing graph coloring in disguise. And so that's one of the many reasons graph coloring is such a ubiquitous, important problem, just like SAT, just like all these other NP-complete problems. They're all equivalent to one another. Okay. In the CPU, a compiler has to do graph coloring. Why? Because it has to register, allocate registers inside the CPU. Arithmetic expressions, that use the same register cannot execute in parallel, even if you have multiple cores or highly parallel pipeline microprocessor, because there'll be clashes on the registers. One's trying to read, one's trying to write from the very same register. And that's going to create hazards or risk conditions. Not a good thing when you're designing hardware. So again, the variables represents registers that are conflicted or not conflicted with each other via some arithmetic expressions, and then you can use register 1 on thread 1 and 3. You can use register 2 for threads 2 and 5 because they don't conflict, and register 3 only for thread 4. And this will minimize the number of registers your compiler is allocating given the hardware constraints. So your compiler, when you run it, trying to optimize machine code, the execution, whether for pipeline kind of execution or multi-threaded execution, needs to solve graph coloring, trying to find the minimum chromatic number of a graph that represents all the constraints of these regular expressions that denote arithmetic operations. So I'm just wanting you to appreciate that graph coloring and chromatic numbers, which is the least number of colors necessary to paint a graph, that's what chromatic number is, happen all the time. Every time you run a piece of code, you invoke the compiler, graph coloring gets solved over and over again under the hood. Now you know. Okay. So it happens a lot. Any questions about any of that? This cartoon kind of depicts a funny situation involving graph coloring in a social setting. Your mileage may vary. P and NP, there's a whole lot to it. There's a whole lot outside it. And I can't imagine how long it took me to come up with this slide here and all the animation involved. But that was a weekend well spent. Any questions about any of this? Graph coloring, transformations, reducing the parameters of a problem, trying to make it easy, see where NP-completeness explodes, at what parameter level, 1, 2, 3, 4, or higher. It takes all kinds, there's all possible flavors of these things. Some problems, no matter how low you reduce a parameter, it's still very, very hard. Some problems, if you increase the parameters, it's NP-complete at all levels. Sometimes the parameter is some weird thing like 12 or 17, although that's more rare. Here we saw an example where the parameter was 4 with respect to degree. That's when it exploded into NP-completeness. Before that, it was relatively easy to ascertain. But you can't make general rules. Generally, it's tricky business. Each thing has to be proven separately, and you can't extrapolate easily from one problem to another. What the parameter would be, what the thresholds are of complexity, and, what makes it easy or hard. It's very problem dependent. Also, approximation schemes. We're going to come up with approximation algorithms such that we're going to, beginning next time, we'll show heuristics or approximations are provably good. We can show that even though a problem is NP-complete, you can solve it to within, say, a factor of 2 of optimal very quickly, within linear, at most quadratic time, and have solutions that are guaranteed to be good with mathematical guarantee. No worse than, say, twice optimal in terms of, say, traveling salesman tour, or the maximum edges across a cut in a graph, or the number of colors needed to paint something. So even though the exact number we'll never know because it's NP-complete, that doesn't mean you can't solve it to within a factor of 2 or a factor of 1.5 or some bound away from optimal, guaranteed within polynomial time, because you can, and we'll show how. In other words, when it comes to execution speed versus solution quality, ideally you want an algorithm that's fast and exact. It gives you an exact solution and does it quickly. So for example, sorting, the short and sweet algorithm for sorting, like merge sort or heap sort, that work very, very fast and they give you the exact answer. And sometimes the exact answer requires a lot of work. Like if you want the exact answer for coloring, colorability, or for satisfiability, or for traveling salesman, we don't know how to do it fast, but you can do it slowly but surely. It'll just take a long time, but you will get the exact answer after enough centuries or millennia of computation. Now, in practice, we don't want to wait centuries or millennia for something to compute. We want an answer today or at most tomorrow. So you want approximation algorithms that are quick and dirty and give you a solution quickly, not necessarily the best solution, but a solution that's good enough. Good enough for you to do your job or deliver your packages if you're FedEx, trying to find a traveling salesman tour through the city, through your destinations. And of course, there are problems that are so hard that even approximating them will take forever. You'll get your answer, it'll be too little, too late. And we won't bother so much with those, although they exist too. So in the next lecture, we'll focus on this quadrant here of the solution space. We'll come up with fast algorithms that give you pretty good answers, approximate answers, but are provably good. At least you have a guarantee that they're no worse than twice the best you can do, even though the best is NP-complete. And those will work in linear time or very, very quickly. And those are very useful. I've written many papers on this topic. Okay. And it's extremely practical. Okay. Any questions about any of this? All right. See you next time.